Okay, so in this problem, we're gonna draw a pedigree and then work out the probability of having a child with an affected child. So this is from chapter 2. It's at the end of the chapter. It's one of the example problems, and it has the solution, so you guys can go over it just in case someone reads it, doesn't get it, and it's better if we go over it together. So the first part of the question up to here gives you general information, and then the question starts here. So they tell you a woman whose maternal uncle has a disease. So usually when they start, they usually tell you about the couple. So here's our couple, and then they tell you something about her maternal uncle. So let's draw her parents, and her mom has a brother, and then those are her grandparents. Okay, so her maternal uncle has the disease, has Tay-Sachs. And yeah, I forgot to mention my conventions. So T, which also the book uses, capital case T is normal, and small case t is a carrier or someone that has the disease. Okay, since it's recessive. So the uncle has it. The grandparents don't have it, but they are heterozygous for the disease. They're carriers, both of them were. That's why the uncle had it. And then trying to determine the probability that she and her husband could have an affected child. So we want to figure out if she's a carrier or not. That's the only way that she will have an affected child. Both her and her husband need to be carriers. Her father does not come from a high-risk population, so it's safe to assume that the father is not even a carrier. Her husband's sister died of the disease at an early age. So her husband's sister had it, which means that their parents were carriers for it. Since she is normal, her husband is normal, her mom is normal, we're not sure if they're carriers for the disease though. But that's the thing. For them to have a child, and this is for not knowing the sex of the child, for them to have an affected child, that's what we're looking for, they need to be carriers. So for her to be a carrier and her husband to be a carrier, we'll calculate the probability of that, but also we need to calculate the probability of the mother being a carrier. The lady's mother. Okay, the couple's mother's ladies. Anyways, I don't know what I'm saying. So you get what I'm saying. So here for this mother, let me get a different color. We know that the grandparents are heterozygous, right? And the ratio for heterozygous genotypic ratio is 1 to 2 to 1. This mother could either be a normal person, not a carrier, or she could be a carrier. This is for the probability of her not carrying the disease. This is the probability of her carrying the disease. This is if she had the disease. Since it's not a colored circle, and she is living and vital and everything, we know that she doesn't have this. So we are considering whether she is carrier or not a carrier, and in this case it's gonna be 1 plus 2, so it's out of 3, right? So the probability of her being a carrier is 2 out of 3. The probability of her not being a carrier is 1 over 3. Okay, for her to pass down the disease to her daughter, we're going to look at the probability of her being a carrier. So the probability of her being a carrier is 2 over 3. Then we look at the daughter here, right? So for the daughter's case, if the mother is a carrier and then the father, we said, he does not carry the disease, it doesn't run in his family, everything's okay. So it's het times homo. We know the ratio for that is 1:1. So the probability of the daughter coming out as a carrier is 1/2. And then for her not to carry the disease, it's also 1/2, but this is the one we're interested in. So the probability of her being a carrier is 1/2, right? And now looking at the husband, his parents are heterozygote for the disease, right? So we do the same thing. It's 1:2:1, and we're not interested in this one. So because he doesn't have the disease, it's not a colored circle, so he can either be normal or carrier. So for him to be normal, it would be 1/3. For him to be a carrier, it's going to be 2/3. So the probability is 2/3. So we figured out the probability for all those parents. And then for the child to have the disease, as we said, both the parents need to be het or carriers. So it's gonna be, right? And the ratio, as we said, is 1:2:1. I know I keep repeating the same thing. And this one is probability of the child having it. It's 1/4. So the answer would be the probability of, wait, let me get a different color. So the probability for this mother to be a carrier is 2/3 times 1/2 multiplied by the father's probability is 2/3 multiplied by their child's probability is 1/4. And final answer would be 1/18. So that's our answer for the probability of the child having the disease. And then so we just solved the question. So we drew the pedigree and we determined the probability of the child having the disease.